Hello students, welcome to wonderful world of organic chemistry today. So I am going to take up the class on the general organic chemistry concepts. Forget about all the functional groups which we are talking into the later classes, but in today's session we will be focusing more about the questions from the general organic chemistry. So what will be the the questions based upon this general chemistry? It will be all about resonance, hyperconjugation, aromaticity, acidity, basicity, how do you write down the structures of Newman projection, Sohas projection. So these are certain things which I will solve the questions. Of course, there are some other concepts such as inductive effect, mesomeric effect, hyperconjugation. So these are some of the topics from the basic general organic chemistry, and I am going to take up the past question papers and we are going to solve the questions from those. Right? Okay, let us solve the questions starting with this, where you have multiple choice with one correct answer. And yeah, here we are, the order of basicity among the following compounds. Okay, so looking at the structures, you'll find nitrogen in each and every structure, right? Of course, but the number of nitrogen varies, but there are presence of nitrogens in every compound. Now they already mentioned that every compound is basic, right? Every compound over here is basic in nature, but what is the order of basicity, in the sense which is more basic to the least basic? What is its order? Just find out. Try to think and answer this question. I'll just show you that okay, there are two nitrogens which has the lone pair of electrons. The second thing, whether those lone pair of electrons are localized or delocalized, means whether they are present on the nitrogen or they are into the resonance. That's what I mean. Localized means whether they are present on the nitrogen, or delocalized in the sense whether they are delocalized or into the resonance. That is second thing. First thing is nitrogen has lone pair of electrons in each and every case because there is no presence of positive charge on the nitrogen. The second point is whether those lone pair of electrons are localized or delocalized. If it is localized, which means all the lone pair of electrons are available for abstracting a proton. That is the property of a base, right? That is the property of a base. That means more the lone pair availability of lone pair of electrons, the faster it can attack a proton. So here also, if the lone pair of electrons are into the resonance, if the lone pair of electrons are participating into the resonance, the availability of lone pair of electrons to attack a hydrogen will be less. So there should be lone pair of electrons. Now look at these structures. Yeah, I have a lone pair of electrons here, 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 everywhere. So which is more basic? Among these, which one do you think is more basic? So I have 1 and 4. Why do you go with 1 and 4? Why do you we consider among 1 and 4? First thing is, I'll say these compounds are more basic because they are aliphatic compounds. Aliphatic compounds. Aliphatic compounds, the lone pairs of electrons are localized, whereas in aromatic compounds, the lone pair of electrons are delocalized. So here the electrons are delocalized, they are into the resonance. So if you look at the order of basicity for these compounds, if you see, here this compound, due to presence of more number of nitrogens, you have 3 nitrogens. The next is 1, here you have 2 nitrogens. Again, then you have 2 and 3, this one and this one. Why? Because this is aliphatic in nature, whereas this is aromatic in nature. Got it? This compound, the compound 3 is aromatic, Why this is aromatic? Because the lone pair of electrons on the nitrogen are undergoing the delocalization. Though there are presence of 2 nitrogens in this compound, only one nitrogen, the lone pair of electrons on one nitrogen are free to attack a proton. In this case, though you have 2 nitrogens, both the nitrogens has lone pair of electrons and both the lone pair of electrons are free to attack a proton and act as a base. Got it, guys? So we will go with the option number C, because the fourth one, which has 3 nitrogens, here you have 2 nitrogens, moreover methyl group, which is a electron donating group. Why among 2 and 3 we are preferring 2? Because 2 is aliphatic compound, which means the lone pair of electrons are not into the resonance, whereas 3 is an aromatic compound and the lone pair of electrons are into the resonance. Of course, not both the nitrogens, one of the nitrogen lone pair of electrons. So it is very simple. The answer is C here. Have a look at this. You have conjugate acid has 3 equivalent protons here. Here you have 2 and here also you have 2. Though it will not explain you the complete answer, whatever the explanation given by me just before this will be the appropriate answer, and option C is the correct answer. Right. Let us move into the next question. Okay, the next question is all about the acidity. So we have discussed about the basicity. For basicity, there should be nitrogen. On the nitrogen, there should be availability of lone pair of electrons, and these lone pair of electrons should be free. That is the concept. What about the acidity? For the acidity, say for example, we can say phenols are acidic in nature, carboxylic acids are also acidic in nature, right? Two things. Phenols are acidic in nature, carboxylic acids are also acidic in nature. Why they are acidic? Means the protons in the phenol, I can say here, here let me draw the structure of phenol. Okay, phenol, if it loses this proton, which means you will get a phenoxide ion. Phenoxide ion is more stable than phenol because this undergoes resonance and stabilizes. In the same way, carboxylic acids also loses that proton, which means it forms carboxylate ion, and carboxylate ion is stable because it undergoes resonance. So the formed structures, either in the case of carboxylic acids or in the case of phenols, are more stable than their parent compounds because these compounds or these structures undergo resonance and stabilizes. That is the reason why they are happy to lose those protons also. Usually any molecule, whether it has a positive charge or negative charge, they are not stable. They can't bear the positive charge or the negative charge on them. But these molecules, the phenols and carboxylic acids, they are happy to lose those protons because even after losing those protons, the negative charge which are present on them delocalizes to reduce the energy. Okay, now you understood. But what is the correct order of acidity for these following compounds? What is the correct order of acidity? Okay, the same thing. They are saying, of course, this is a question from JEE Advanced 2016. They are saying that all the compounds are acidic, but which is more acidic? What do you mean by which is more acidic? Which is ready to lose a proton, right? Which is ready to lose a proton, that is more acidic. So which is ready here to lose a proton? Look at this, which is very ready to lose a proton, which can form a stable complex. Think about hydrogen bonding, think about presence of ortho, meta and para hydroxy groups. Okay, have you heard about intramolecular hydrogen bonding? Can you tell me any compound where intramolecular hydrogen bonding is present? Generally, we have hydrogen bonding wherein which oxygen, right, or nitrogen or fluorine, that is attached to a hydrogen. So, intra and inter, there are two types of hydrogen bonding. Intramolecular hydrogen bonding will be possible in the same compounds, right, within the same compound. Say here, I am just showing you an example where intramolecular hydrogen bonding is present. Here we are talking about, look at this, OH and this is CHO. So, the oxygen of this can bond, that is hydrogen bond, with the aldehyde of this, intramolecular, within the molecule. In the same way, if you look at this one, have a look at this compound. This compound can make a intramolecular hydrogen bonding. Let us see how can it do. Okay, I have C double bond O, O, H. Here I have phenol. So, this oxygen can form hydrogen bond. Is it? Can you look at this, guys? This part of the molecule, it is forming a hydrogen bond, which means hydrogen bond makes the molecule more stable. Here I have only one hydroxy group. What if there are presence of two hydroxy groups here? So, here if you see this molecule wherein which I have benzene and this is your carboxylate ion, here this is one OH and this is another OH, means upon losing a proton, this one, it will be stabilized because of this reason. You have C double bond O and O minus, which means this minus charge will be delocalized, so that minus will develop on this oxygen also, which means you have a OH over here and you have a OH over here. So, this hydrogen bond or this hydrogen bond, because the negative charge is delocalized between these two oxygen atoms. That is the reason why this is more stable. Even after losing a proton, it is stabilized by hydrogen bonding. So, the compound number 1 is most stable or it is more acidic because no one is ready to lose a proton, but this compound happily loses a proton because even after losing a proton it will be stabilized, it will be happy with the least energy because of the intramolecular hydrogen bond. So, where is the option 1? Right, either answer can be A or answer can be D. B and C cannot be the answers. The next, this compound number 2, because of the hydrogen bonding again, you have two hydroxy groups here, but here only one hydroxy group. After 1 it should be 2, so the option is A and we are rejecting this as well. Is it clear to all of you? The first one, this one, next is this, last will be this, because this is the OH group is present far away, right, the OH group is present far away and here it is present just alternatively, that is it. So, it is 1, 2, 3, 4 the same order. The correct option is A. Okay, we will move on to the next question quickly. It's all about hyperconjugation, right, very interesting, right. What is hyperconjugation? Is also called as Baker-Norton effect, right, all about the alpha hydrogens. The hyperconjugation stabilities of tertiary butyl cation and 2-butene respectively. Okay, two compounds, one is tertiary butyl cation and second is 2-butene. They have given you the two structures and these two structures, and they have already mentioned that these two structures are stabilized by hyperconjugation. but what sort of stability? Whether it is sigma to p, sigma to sigma star, sigma to p, or sigma to sigma star, or sigma to pi star. So, what sort of stabilities? Let us have a look at those structures. Tertiary butyl cation, okay, I have a carbon, right? Tertiary butyl methyl groups are present, okay, yes, tertiary butyl carbocation. The next structure is 2-butene, okay, I have 1, 2, 3, 4, and the second carbon you have a double bond followed by CH3, CH, CH and CH3. Okay, what is alpha hydrogen here? What is an alpha hydrogen? Alpha hydrogen is the one which is present next to the carbon. Okay, firstly you should understand what is an alpha carbon. Before understanding what is alpha hydrogen, you should know what is alpha carbon. What is alpha carbon? The carbon present next to the positive charge species or the functional group. That is the alpha carbon, and the hydrogens attached to the alpha carbon, those hydrogens are called as alpha hydrogens. So, here this carbon is not an alpha carbon. The carbon next to this carbon, because this is the carbon bearing the positive charge. So, this one and this carbon and this carbon, these 3 carbons are the alpha carbons, and the hydrogens attached to these carbons are called as alpha hydrogens. Basically, hyperconjugation is delocalization of alpha hydrogens. Why is the positive charge here? Because carbocation, what is the valency of carbon? Carbon has 4 valency, but due to loss of 1 electron you have an empty p orbital, which means I am drawing this one, helix. So, you have a hydrogen here, hydrogen here, hydrogen here, delocalization of sigma bonds. That is what alpha hydrogen or delocalization of sigma bond. How it is delocalizing? This hydrogen here, upon delocalization you have a structure. That means the sigma bond is moving to empty p orbital. A sigma bond is delocalized to empty p orbital. You can see that this is p filled, sigma to p filled. P filled it cannot go, it is an empty p orbital. Sigma to sigma star no, but sigma to p, empty p orbitals. That's this sort of delocalization is hyperconjugation. Option A, even in the case of this one, sigma to pi star, why? You have the double bond present here, the carbon present next to the functional group in this case is the alpha carbon, and these hydrogens are the alpha hydrogens, So, here you have CH3, CH double bond, CH, of course CH3. So, one delocalization, what is going to happen? This delocalization, what is happening? A sigma bond is converted to a pi bond, and this will delocalize to this one. So, that is the reason why, see, upon delocalizing what happens? This bond is happening, that means there is no bond between a carbon and hydrogen after delocalization of sigma electrons. That is the reason why hyperconjugation is also called as no bond resonance. Hyperconjugation is also called as no bond resonance because the sigma electrons is lost. If a pi bond is lost, you will be having one sigma bond, but if a sigma bond is lost, there is no bond between the carbon and hydrogen. That is the reason why here it is sigma to pi star, electron delocalization. Is it clear to you? The hyperconjugation stabilities in JEE Advanced 2013, we have found out that in tertiary butyl cation, it is because of sigma to empty p orbital delocalization. Here again sigma to pi star electron deconfiguration. Okay, we will quickly move on to the next question. Right, this we have seen again multiple choice questions with one or more than one correct answer. So here it is not only one correct answer, you have more than one correct answer. We have to be more careful in solving the questions. Right, very easiest question that you have got in JEE Advanced 2017. What the question is all about? The nomenclature. But where we are studying it, having more than one option, do you think a compound, that IUPAC compound of an organic compound has more than one name? Of course, the closest names, because if you look at the structure of the benzene, it has the functional groups. There is no presence of any functional group. If you have any functional group, you will be having only one name, but you do not have any functional groups here. Those both are the prefixes, right? So here methyl and chlorine both are the prefix only. They do not have any functional group here. That is the reason why you can have multiple names. What are those names? Find out what are the answers, because you have more than one correct answer in this one. More than one correct answer. What are the correct answers? Let us rule out one by one. 4-methyl chlorobenzene. Okay, let us write down here, give the numbering, whether number 1 will be this carbon or this carbon. Which is the carbon number 1? I will prefer the carbon number 1 is this one, it is not this one, because the substituent is chloro, but here the substituent is methyl. So based upon the alphabetical, C comes first, then goes me. Here this will be 1. Okay, 1, this is 2, this is 3 and 4. So 4-methyl chlorobenzene, this can be a correct answer. Yes, 4-methyl, overall it is a chlorobenzene. Then 4-chlorotoluene, right, I can say when I have taken toluene as a functional group, right, toluene as a functional, this I am taken as toluene, 4-chlorotoluene, 1-chloro 4-methyl benzene. Okay, 1-chloro and 4-methyl benzene, yeah, 1-methyl 4-chlorobenzene. This cannot be answered. Based upon the alphabetical wise, methyl cannot be given as number 1 position, it is always chloro. So this cannot be your answer. Option A, B and C, all these 3 are right for this. Yes, options A, B and C based upon the numbering. Look at the numbering. So basic funda, you should know how to name the organic compound based upon the alphabetical sequence. That is the only thing we can come up to this answer. Let us move on to the next question. Okay, this is something related to hydrogen bonding. Hydrogen bonding plays a central role in the following phenomena. So they have given you, right, 4 phenomenons, and they said that in all these 4 phenomena, hydrogen bonding is the one that is playing the crucial role. Okay, so whether it is true or not, we have to find out. The first is ice floats in water. That means what they are saying, ice floats on water, it is because of the hydrogen bonds present in the ice. Is it right? Ice floats on water, is it because of due to presence of hydrogen bonding in ice? Is it so? Okay, we will come to that. Higher Lewis basicity of primary amines than tertiary amines in aqueous solution. So they are saying primary amines are more basic, okay, primary amines are more basic than tertiary amines. Okay, first, do you agree with this? Primary amines are more basic than tertiary amines, is it true? Yes, primary amines, of course they are more basic than tertiary amines because of steric hindrance in the tertiary amines, right. But amines, the higher Lewis basicity of primary amines than tertiary amines in aqueous solution is because of hydrogen bonding. Is it true? The reason we know, okay, that tertiary amines are less basic because of the steric hindrance, but primary amines are more basic. Is it because of hydrogen bonding? That's one thing, again we have to figure it out. Okay, formic acid is more acidic than acetic acid. Formic acid is more acidic than acetic acid. Firstly, let's forget whether hydrogen bonding is involved here or not. Just tell me whether this is true or not. I will say, yeah, formic acid is more acidic than acetic acid because look at the structure of formic acid here. Formic acid, yes, is more acidic than acetic acid because methyl is a electron donating group and it stabilizes this bond between the oxygen and hydrogen. So, the release of hydrogen here is delayed a bit than here, but is it due to hydrogen bonding again? Okay, the fact is true, but is it due to hydrogen bonding? Dimerization of acetic acid in benzene. Okay, acetic acid dimerizes in benzene. Okay, anyway, acetic acid, it exists in dimer form in benzene, but is it due to hydrogen bonding? So, these are the 4 facts what we need to see. Look at the first one, ice floats in water. Yes, ice floats in water. Look at the structures of water. This is the structure of water. What happens? Heat the water molecules move away. Okay, take water in a glass and drop ice in it. What happens? Ice floats on water. Why do ice floats on water? Because of the presence of hydrogen bonding between one water molecule and another water molecule. The hydrogen bonds present between the one water molecule and another one. So, yes, ice floats on water because of the hydrogen bonding present. The first fact is true. What about the second one? Higher Lewis basicity of primary amines. Yes, again this is another case where in which you can see this is amine. When amines are added to water, it forms a quaternary salt, this one. This quaternary salt will be stabilized by water, whereas in this case it cannot be stabilized because of the bulkier alkyl group surrounding it, whereas in this case it is stabilized again by hydrogen bonding. So, the second fact is true. The third one, it does not make any sense. It is not because of the hydrogen bonding, but it is because of the electron donating group, which means plus I effect, that is inductive effect. Formic acid is more acidic than acetic acid because of inductive effect, not because of hydrogen bonding. And the last one, dimerization of acetic acid in benzene. Yes, dimerization, yes, the structure. This is one acetic molecule, this is, yes, this is the structure of one acetic acid, a structure of another acetic acid. When they both dimerizes, which means there is presence of hydrogen bond between the 2 acetic acid molecules. So, except option C, A, B and D are the right answers. So, this is the question asked in JEE Advanced 2014, of course very simple, a bit logical. Okay. Alright, this is something about the isomers, number of isomers that we can find out. The correct combination of names for isomeric alcohols with molecular formula C4H10O. Okay, what they have given here is they have given you the molecular formula which is C4H10O. Of course, alcohols or ethers what you get. Anyway, the names given here over are alcohols, everywhere it is a alcohols. So, let us say this is an alcohol. When you write down the structures of different isomers of this molecular formula, they have given you the names, whether these are the correct combinations. That means you have a common name on one side, IUPAC name on the another side, common name with their IUPAC names, whether these two names are similar or different. Without writing structures, can we figure out whether they are correct or not? Tertiary butanol and 2-methyl propane 2-ol. Tertiary butanol means but, you have 4 carbons here, 2-methyl propane 2-ol. Yeah, we have 1-methyl prop, 3 carbons, totally 4 carbons in this case. Here tertiary butanol, again they have 4 carbons, 1,1 dimethyl ethane 1-ol. Okay, here as well you have 4 carbons, fine. N-butanol, butane 1-ol, it is correct. Isobutyl alcohol, and this is isobutyl, where you have the 4 carbons, 2-methyl propane 1-ol, again 4 carbons. Of course, the number of carbons in each and every case it is similar. Then you need to look at the structures, whether these structures are exactly replicating the names. In this case, okay, let me come out N-butanol and butane 1-ol, that is the right answer. Without drawing the structures we can say. What about tertiary butanol? Tertiary butanol is something like this. You have a carbon wherein which you have 3 methyl groups and OH. All these 3 are methyl groups. How do you name it? If you see, this carbon will be 1, then you have CH3 here. So 1,1 dimethyl ethanol, 1,1 dimethyl ethanol, which means this is correct but this is wrong. Are you getting it? When you write on the structure of tertiary butanol, tertiary butanol structure, when you write on the structure, the IUPAC name of this one is 1,1 dimethyl ethanol, but it is not 2-methyl propanol. So, the option 1 is wrong. And here also isobutyl alcohol and 2-methyl propanol. You can see here isobutyl, you have 2-methyl, 1 yes. So, this part is a isobutyl part. So, isobutyl and 2-methyl propanol, yes, this is the correct. So, this is how you need to write down the isomeric alcohols structures. Okay, this is something which is regarding the N, O, P and Q, that means you have been given with the Sawhorse projections and Newman projections. Yes, Sawhorse projections, here I have Newman projections. Now, the questions is something like, you know, NOPQ, yeah, NOPQ they have given 4 and with respect to M, what are they? For example, M and N are non-mirror image stereoisomers. Non-mirror image stereoisomers means they are diastereomers. M and O are identical. M and P are enantiomers and M and Q are identical again. How do you find out? We cannot figure it out just by looking at the Sawhorse projections or Newman projections. You should know how do you write down these structures in Fisher's projection formulas. Fisher's projection. Convert all the structures to Fisher projection formulas, right? You have M, N, O, P and Q. Once you write down in the Fisher projection formula, then you start comparing with, right? So, I have converted the Sawhorse projections including the compound M as well as the Newman projections into the Fisher projection formula. So when I have converted, now look at this, M and N. What is the relation between M and N? What is the relation between M and N here? I have this compound C and H3 here. Do you think M and N are non-mirror image stereoisomers? Yes. M and N are non-mirror image stereoisomers, which means they both are diastereomers. In the same way, M and O are identical, is it? M here, O here, they both are identical, yes. They both are identical molecules. The next one, M and P are enantiomers. Enantiomers means exactly opposite, it has to be M and P. You can see these two OH are here, but these two OH are here. Exactly opposite, yes, they are enantiomers. No need to find out the configuration, no need to find out the absolute configuration whether it is R or S, just by looking at the structures. You have OH groups on the left side here, OH groups on the right side here. Then M and Q are identical, which means the structure should look alike, the same thing. Of course, you have chlorine and methyl on the same positions, even this part is same, but this part is not different. M and Q are diastereomers, they are not stereoisomers, sorry, they are not identical. M and Q are not identical, they are diastereomers. So what is most important for this question? How can you convert? That means, of course, we have A, B and C, three options are right, but the last option M and Q are identical is the wrong option. But the most important part of this question is, how would you convert a Sahar's projection to Fisher projection, or how do you convert a Newman projection to a Fisher projection? That is quite important. And when you have to look at the structures, whether it is present in the form of Y or in the form of inverted Y. So when you are converting this sort of structures into Fisher projection, you should be at most careful, even by rotation of single bonds. If you are missing it out, then you will end up with a different answer. So converting these structures into Fisher projection makes a more important thing to solve this question. Hope you understood. We'll move on to the next question. Right, this question is all about three topics: aromatic, anti-aromatic, non-aromatic. Okay, what do you mean by aromatic compounds? Of course, most of you must be knowing aromatic compounds. Aromatic compounds should fulfill four characteristics. What are those? They are cyclic in nature, right? Cyclic. They should have a planar structure, delocalization of double bonds or pi electrons, delocalization. The most important thing is follow Huckel's rule, which is 4n plus 2 pi electrons. But when I mention as anti-aromatic, against aromatic, anti-aromatic compounds, the first three properties should be similar, in the sense this one, the next one, the next one should be very similar. But this one, that is Huckel's rule, it is not obeying. That is why it is called as anti-aromatic, which means here it has 4 pi electron system, the multiples, like when you have 4 electron, 8 electron, 12, 16, 20. So this part of this is anti-aromatic, whereas this one 4n plus 2 will be aromatic. The last one is non-aromatic, which means none of these will be fulfilled. Then we can say it is a non-aromatic. Okay, I have a question for you. When do you say that a compound is planar? How can I say by looking at the structure that this is a planar molecule? just by looking at the structure, how can we say it is a planar structure, which means all the carbons in the not only carbons or oxygen or nitrogen, whatever, all the atoms in a given structure should have sp2 hybridization. If every atom in the given structure has sp2 hybridization, then I can say that the given compound is having a planar, trigonal planar, right? Now, shall we solve this one? Though they are asking you to find out which of the following compounds in pure form are unstable at room temperature. What are unstable? Anti-aromatic compounds are extremely unstable. Anti-aromatic compounds are unstable. Aromatic compounds are stable because of the delocalization and they reduce their energy, ring current, what we say. Whereas non-aromatic compounds, all the alkanes, alcohols, whatever the straight chain compounds, whatever you take, those are non-aromatic compounds, even they are stable. But anti-aromatic compounds, this is one thing which are highly unstable because they tend to lose their energy continuously. So remember this one, anti-aromatic compounds are highly unstable, which means they are asking you to find out which are anti-aromatic compounds here, because they are unstable at room temperature. Tell me what is the first one, where is the aromatic, anti-aromatic or non-aromatic? I will go with, do not say this is a 4 pi electron system, okay. Even though it is a 4 pi electron system, there should be delocalization also, right. Even though it is a 4 pi electron system, there should be delocalization also, it should have planarity also. But this carbon is sp3 carbon, of course even this carbon is sp3 carbon, which means this compound is non-aromatic, in the sense this is not a unstable compound, it is a stable. Whereas compound B is unstable, means it is a anti-aromatic compound because it is cyclic, it is a planar, because every carbon has sp2 hybridization. Delocalization is present, yes, this bond can delocalize like this, delocalization is present, and 4 pi electron system, yes, number of pi electrons here are 4, it is a 4 pi electron system. So this one is a anti-aromatic compound. Looking at the structure C, what about this one and what about this one? This is again anti-aromatic compound, which means this is also unstable. Why? Because 4 pi electron system, of course do not consider the double bond which is present outside the ring, because it is not participating in the delocalization process. This bond is not participating in the delocalization process, it is present outside the ring system continuously. Whereas this carbon is sp2, so it is anti-aromatic compound. And the last one, this one is 6 pi electron system, this is a aromatic compound. So the options here are option B and C, because they are anti-aromatic in nature. Anti-aromatic compounds are unstable. Is it clear to you? Okay, I will rush up to the next question because it is almost similar to this question. About the subjective problems we are starting with. Anyway, we have plenty of compounds here. Let us figure out what are aromatic compounds in this. I will give a minute time for you, just find out what are aromatic compounds in this. Meanwhile, I will show you which are anti-aromatic or non-aromatic also. Okay, here I will go with anti-aromatic compounds. 8 pi electrons, you have 2, 2, 2, 2, 8 pi electrons. The next one, you have 4 pi electrons, again anti. This one is aromatic. Of course, you have 2 pi electron system, this is one. Cyclopropyl cation. Cyclopropyl cation is one of the such exception from 4n plus 2 pi electron system, wherein which though it has 2 electrons, still it is aromatic because delocalization is present and every carbon is sp2. This is non-aromatic. This is non-aromatic, whereas this one is aromatic again. Every carbon is having a sp2 hybridization and even carbocation is nothing but sp2. This one is aromatic. Look at this. This one you have sp2 hybridization and 4 pi. Okay, this is anti-aromatic. This is 6 pi electron aromatic system. You have sp2 carbons here, sorry, sp3 carbons in these two cases, non-aromatic. This one is nothing but your phenanthrene compound, it's aromatic. Okay, have a look at all these structures. Everywhere we have written, so anti-aromatic compound, just because you have 8 pi electron system, this is anti-aromatic compound, you have 4 pi electron system, multiples of 4. This one, though it has 2 pi electron system, as I said you, this is the only exception from the Huckel's rule that it is a aromatic in nature. The next one, you have sp3 carbons here, so it is non-aromatic. Here you have 6 pi electron system and delocalization is present, so it is aromatic again. In this case, this is a 4 pi electron system. The next one, here it is 6 pi electron system, of course, because this negative charge is also involved in the delocalization. Here you have sp3 carbons here, so it is non-aromatic. This is the structure of phenanthrene. You have everywhere the delocalization is present, aromatic, sp2 hybridized carbons are present everywhere. So you have 5 compounds that are aromatic. These are the 5 compounds. Of course, we have also seen what are non-aromatic and anti-aromatic compounds as well. Clear? We will move on to the next question quickly. Okay, the maximum number of isomers that are possible on monochlorination of this compound. On monochlorination of this compound, right? So how many different carbons are there here? This is a carbon, you have hydrogen here. That means I can get replacement of this hydrogen, I will get 1 chlorine, replacement of these hydrogens, that is another product, here 1, here 1. Of course, if you replace here also, both are ethyl groups, right? Both are ethyl groups, so you will be end up with same products, which means 4 isomers I can get, which means I will show you. You have, yeah, C, H, CH3, and here you have CH2, CH3, here you have CH2, CH3. Now start replacing the hydrogens. When I replace this one, I will get a compound CCl, right. The next one, replacing this one, I will get on CH2, Cl. The next one here CH, Cl, then this will be as CH3 again. The last one will be like CH2, CH2, Cl. During this process, though you are getting only 4 isomers, look at the any carbon if it has a chiral carbon or not. That is most important. Of course, we are ending up with, because how many different types of hydrogens we have, okay, how many different types of hydrogens we have, that many different number of products you get. I have 4 different hydrogens, 4 different hydrogens. So I will get 4 isomers, but during this process I may have isomers. Look at this. In this case, when I have replaced this chlorine, okay, this hydrogen with chlorine, immediately there is a stereocenter generated. There is a stereocenter generated, which means this has one more isomer, because this is a chiral carbon. So I have a 2 isomers in this case. This is a 2 isomers, and when I have replaced this Cl, immediately there are 2 chiral centers generated, which is giving me 4 isomers. So this itself is having 6 isomers, and the rest 2 what we have seen, that one hydrogen of methyl group is replaced with chlorine, and the hydrogen that is directly attached to carbon also has replaced. So though we have only 4 isomers, but if you forgot identifying the chiral carbon, then what happens? You will end up with only 4 isomers, but there is presence of one chiral carbon here, which is giving you 2 isomers. There is presence of 2 chiral carbons, which is giving you 4 isomers. So total 8 isomers are possible for this. Got it? Okay, find out this. This is very simple. You need to find out the total number of contributing structures, that is hyperconjugation structures. How many hyperconjugation structures are possible in any given compound? How many hyperconjugation structures are possible? That means how many number of isomers are possible. It is nothing but how many alpha hydrogens you have. Okay, number of alpha hydrogens is equal to number of hyperconjugation structures. That's it. Number of alpha hydrogens is equal to number of hyperconjugation structures. So how many alpha hydrogens we have? This is the carbon. So the next carbon is called as alpha carbon. This is alpha carbon, this is alpha carbon, and this is one alpha carbon. But this one is a beta carbon. This is beta, this is beta, and this is beta. So I have, there is one hydrogen here, 1, this is 3, and this is 2, which means 6 hyperconjugation structures are possible for this molecule. That is very simple. Number of alpha hydrogens is equal to number of hyperconjugation structures. So I have 1, 3, and 2, total 6. If you count these hydrogens, no, those are beta hydrogens, means they are attached to a beta carbon, not the alpha carbon. So any queries so far, what has been taught to you? So we have come to the end of the session. So that's all from this session, all about the acidity, basicity, then hyperconjugation structures, resonance, aromatic, anti-aromatic, non-aromatic. So this is something which is regarding the general organic chemistry, and I have discussed all the previous most of the questions from the past papers. So this is all for the today's session. Thank you guys.